Section 7.3 is on page 361, talks about properties of Laplace transforms. So now that we know the definition, we're going to use a table. Instead of integrating, Laplace put all of these solutions in a table in which you could use instead of integrating and be able to solve a differential equation without using, you're theoretically using calculus because you're using the table, but instead use the table instead of integration. So first things off, if you apply the Laplace transform on, if the Laplace transform applied on f of s is known as f of s, then the Laplace applied on e to the at times f of t, that would be capital F, which is f of s, but shifted by a units. So the Laplace applied on f of t is simply f of s, and a lot of books call it y of s, which is the same thing. Let t be defined from 0 to infinity, and f prime is piecewise continuous on 0 to infinity as well, with both exponential order alpha, where s is bigger than alpha. The Laplace applied on a derivative is s times f, which is the Laplace applied on f of t, minus f of 0. And if you apply it on mth derivatives, this is the formula for order derivatives that we need, but we only work or focus on second derivative in this case. And if we touch on a third derivative, I'll point that out. Now I already uploaded this formula sheet for you. It's already in files. You could download it and have it next to you on the next exam in the final. And it lists the Laplace transform applied on what we did in section 7.2. And on the bottom of it, you'll notice I applied the definition on the very bottom, and I applied the Laplace on a derivative and the Laplace on second derivative. That's all we need for this course. If we need for more than second derivative, I'll provide that as well. And just that you know, when you apply the Laplace on the sum of two functions, that would be the Laplace applied on the first function plus the Laplace applied on the second function, where if a is a constant, you could drag that out and multiply it by the Laplace, and same thing with b. So here a and b are constants, and Laplace being applied on two functions. This is linearity, and that's how we're going to play this game. And that's going to be listed. Now on this table, you notice this formula right here, the Laplace applied on Tn times, oh, by the way, I forgot to mention, the Laplace right there applied on e to the at f of t is listed on the formula, and that would be, let me see what number that is. That's number 12 right there. And the theorem I just showed you right now, the last theorem, is number 14 listed on this formula sheet. So there it is. That's number 14 on the formula sheet, and that's number 12 on the formula sheet. Here's the catch. You're going to be able to use the table. So determine the Laplace transform of the given function. So if we determine the Laplace transform of the given function using table 7.1 is the table I'm providing. That's this formula sheet. And the properties of transform, all the properties you need are listed on this table. And again, you could print that out and use it on the test. And number 12 to 20 is appropriate trigonometric identity. We'll get to that in a minute. Now, I want to apply, this is on page 365 in our book. So if I look at this, I have two ways of doing this. Either I do the Laplace applied on 3t squared minus e to the 2t is the integral from 0 to infinity of e to the st times 3t squared minus e to the 2t dt, and provide with all of that and do what we did in the previous section. Or I could simply say, well, Laplace did that for us already. So the Laplace applied, that would be the Laplace applied on the 3t squared minus the Laplace applied on the e to the 2t. I just showed you the linearity property of Laplace, and by doing so, the 3 is a constant. And now here's the catch. I'm looking for t squared. I notice number 3 has t to the n. T squared, so n is a 2. It's going to be 2 factorial over s to the 2 plus 1, which is s3. So that's going to be 2 factorial over s3. The catch is you have to tell me what did you use, and we used number 3 on the table. And you do that in the homework, you do that in the exam, minus the exponential of e to the 2t. If you want to apply Laplace on e to the at, it's 1 over s minus a. Since a in this case is a 2, it's 1 over s minus 2. And in this case, we use number 4, as you see. So on your homework on the test, you don't write these numbers, you get no credit. Of course, you could simplify that if you wish, but that's sufficient. And if I apply the Laplace on number 4, I'm looking at 4 times minus 2 times plus, and Laplace applied on t to the 4th. That's number 3, n equal 4. 4 factorial over s to the 5. And t squared, n equal 2, 2 factorial over 1 more s cubed. That is by number 3. So you make sure you tell me you use number 3. And on 1, if you want to use 1, that's right there, number 1. The Laplace applied on 1 is 1 over s. And that is by 1. And yes, you're going to have to state that on every problem that you use Laplace on. And if that's an issue, then don't use the table and use the definition and go from there. All good. I don't mind. Let me fix this really quick. There we go. And now let's apply the Laplace on number 6. And that's going to be, let's see, e to the negative 2t sine of 2t. E to the negative 2t sine of 2t, that's number 7. So there's an angle and there's the power. E, they're both 2 in this case. So that's going to be 2 divided by s minus 2. 2 divided by s minus 2 squared plus b squared, the angle squared, which is 2 squared, that is 4. This is by 7. Again, 7 is right there. Plus, and t squared e to the 3t, we need to find a t squared times e to the tt, it's number 9. So the power is n, that is n factorial or over 1 plus more, so the power is 2. That is 2 factorial over 1 more, which is 3, and it's going to be s minus a, if you notice. So a is 3, s minus 3. And this is by, what number was that? Number 9. There you go. And that's all you have to do. Again, the alternative to all of this mess is really simple. Do the integration, spend all of that time, and you get the same answer. Those are the only 2 alternatives. You want to use the table, I have to make sure that I see that table. We don't have this listed in our table, so there's a way of doing that. And now if I apply the Laplace on this, that will be the Laplace on 1, that was 1 over s, that was number 1, plus 2 times the Laplace on e to the negative s, 1, the s minus a negative 1 is plus 1, and I believe that's number, I think that's number 3. Let me double check. 4, I'm sorry, 4, that's number 4. Plus 1 over s plus 2, that's also 4. So every time I use that table, I have to quote it. And you can't use another table. It has to be this table with these numbers. If I apply the Laplace on this, that would be, and I need to eyeball something like that. So there's a t to the n, e to the negative, so 7 and 8 don't have a t to the n. T to the n happens to exist in number 3. Number 9, but there's no e. And number 14. 14 says, if you have t to the n f of t, it's negative 1 to the n. It's t to the 1. So negative 1 to the 1 times the derivative. How many derivatives? Let's see really quick. N derivative. So first derivative of e to the 2t cosine of 5t. Yep. So that's all we have to do. And if we work this out, how would this be? Let's see what that is. Actually, this is going to be the derivative of f, which is, let's see, that is s minus 2 shifted by 2 and s minus 2 squared plus 5 squared. So again, if you really pay attention, every time there's an e, there's a shift. Every time there's an e. Without an e, this is it. If you add an e to the at, you shift s by a. You shift s by a and a cosine. So here, t to the n, negative 1 to the n times the derivative if you apply on f of t. And there it is. All what I have to do is take a derivative of this, which is a derivative of the top times the denominator minus s minus 2 times derivative of this over the denominator squared. If I take a factor out, oh, I can't factor any of these out. Let me check. That's kind of odd. Okay. S times s minus 2 squared plus 25s minus 2 times s minus 2 squared. So those are the same. If I factor that out, I'll have s minus 2 plus 25s. Okay, and that becomes a cubed, and there it is. We want to find the Laplace transform applied on the following. Well, we figure out that, look, the sine of 2 theta is twice the sine of theta cosine of theta. So the sine of theta cosine of theta is the sine of 2 theta divided by 2. So this is the sine of 6 theta divided by 2. And if I apply the Laplace on that, so this is second semester calculus really, or some trigonometric identities. This is going to be the 1/2, and sine of 6 theta by number 5, that is 6 divided by s squared plus 6 squared. Of course, you could reduce that to 3 over s over 6, whatever you like, whatever makes you happy. That's not an issue. So we don't need that right there. And let me just shift a few things. I thought I would need a lot more space. Obviously, I don't. So that's 1. Number 14, I'm hunting for a sine squared. I don't see a sine squared anywhere. So what I remember that, wait a minute, this is e to the 7t. This is 1 minus the cosine of twice the angle divided by 2. So this is 1/2 times e to the 7t minus e to the 7t. Oh boy, I forgot to mention, this was done by 5. There, I would have lost a lot of points. And this one was done by, I believe, 14, right? 14. There we go. So make sure you put it on, you circle it so I could see it. And now if I apply the Laplace on this, that would be 1/2 times 1 over s minus 7 minus, oh, and this is going to be cosine. If I apply the Laplace and cosine of 2t, that will be s over s squared plus 4. I'm going to shift everything by 7. And that's how the game is played. Of course, this is by trying to do math. I think this is 4 and this is 8. 4. Yep, 4 and 8 was a cosine. It's a cosine. Perfect. Okay, there it is. So, using the Laplace transform makes this process, integrating these functions, is a lot of fun. And you know, if you have a lot of free time, I strongly suggest you try some. Wait, did we just do 16? Oh no, okay, 16. The same idea with this. Here you can't find sine squared, so you say, okay, you know what, that's t times, and if I work this out, 1 minus cosine of 2t over 2, and cosine squared is 1 plus cosine of 2t divided by 2. So that is 1/2 t minus t, that cosine of 2t. And if I apply the Laplace on that, I'll get 1/2. And the Laplace applied on 7 is 1 over s, n is 1, 1 plus 1, right? That would be by 2, I think, or 3, 2, by 3, no, 2, 1 over s squared. You know, they have, you could use 3 and say n equal 1, or just say 1 over s squared, so by 2, minus a t cosine. Well, that's, we have to go to 14 again, because t times a function, that's going to be t times the derivative, so that's going to be negative 1 to the n times the derivative. And what is the cosine of 2t? That is s divided by s squared plus 4, and this is by 14, and the rest is just some calculus. Plus 1, derivative of the top is 1 times the bottom minus the top times derivative of the bottom, all over the bottom squared. And that is 1/2 1 over s squared plus 2s squared plus s squared is negative s squared plus 4 over s squared plus 4 squared. You know, whatever that gives you. And I believe that's pretty much it for this section. That's the last example I have. Yeah.